Maybe not. All right, so what we did yesterday, we are beginning to list. We're beginning to list the Taylor series that you need to memorize, and that includes the general term. So it's called the general term, or the nth term, or the rule of sequence. They're all kind of synonymous, but it's the function of n that generates each term. So there's the sine, and the cosine, which I'll draw in pink since that's the color I'm in. You can either take the derivative of sine, which is just kind of a nice way to show that it is cosine, but you don't want to memorize it by taking the derivative sine. So, cosine is what? Even or odd or neither? Cosine is even. So it starts with the even term, which is the constant 1, and then like sine it alternates. So then minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. And notice, even though the next term would be negative, I can put plus dot, dot, dot. It still doesn't matter, because remember, subtraction is just adding the opposite. If I were to actually list it, though, I'd have to have a negative. Plus, and now we'll do kind of the same thing. We'll write the general term in here. It's negative 1 to the n. I may come back and adjust it, n plus 1. But now to generate even numbers, it's not x to the 2n plus 1, but rather x to the 2n. And then it's just going to be that same number, 2n quantity factorial, and then plus dot, dot, dot. And we'll quickly check to see if our n's line up in terms of generating both the number and the sign. So when n is 0, I get negative 1 to the 0, bless you, which is positive. And then x to the 0 would be 1, 0 factorial is 1. So it works, all right? If my sign was off from the magnitude, I could just put a little plus 1 or minus 1 on the end to adjust it. So you don't have to say what n you start with when you do the general term. You just have to make sure that they coincide. If you brought that back together with the sigma, that's when you do have to name the starting value. So it's really the same series. And we get this. Now the sine and the cosine, of course, you can look at the power series rule of sequence and realize they're centered at 0, right? Because they're just x to a power, not x minus something to a power. So these are both centered at 0. And without having to do the ratio test, the radius of convergence for both of these is, guess what? Or what would be the domain of the power series? For what values of x do the series converge to the actual function? Thank you. All real numbers, yeah. So sine and cosine, as well as e, when you include infinitely many terms, they become exactly the function sine and cosine and e. So speaking of e, let's go ahead and list it. E to the x is going to be, e for easy, hopefully still, right? 1 plus x squared over 2 factorial. Yeah, and then plus x cubed over 3 factorial plus dot, 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 plus. And now it looks like they don't alternate, so we don't need an alternator. It's just going to be x to the n over n factorial, yeah, plus dot, dot, dot. And when we start with n equals 0 again, we get x to the 0 over 0 factorial, which is 1. So if you were to write it in sigma notation, you would need to say where you start, n equals 0 to infinity, x to the n over n factorial. Could I also write the general term, if I didn't want to do it as x to the n, could I write it as x to the n plus 1 over n plus 1 factorial? Would that also work? Yeah, this would actually work. For sure, it captures the pattern, but now I wouldn't start at 0. I would start at, actually, I would have to start at negative 1, right? So typically we don't like to start with a negative number on the sigma. So I could do n minus 1 over n minus 1. And again, that would still capture the pattern, but now my sigma would start with 1, okay? So the rule of sequence, when it's listed as a general term, as long as it captures the pattern for some n, it could be anything. But when you write the sigma again, that's when you actually have to specify what we start at. So we might as well just go with the easiest ones, which is just x to the n. So again, go ahead.
So why didn't you do that for the sine function?
We could do it for sine as well.
Where it says 2n plus 1 factorial.
I could change 2s plus 1, both of them for sine. I could easily right here change both of those to 2n minus 1. And it would still capture the pattern. I would just have a different starting value over here on my sigma. okay? It's really nice to start with either 0 if the series is defined at 0, or 1 if it's not. 0 and 1 are kind of the two nicest values to start with. All right, so memorize these three. Memorize these three. Okay, so now to get on to example 3, it says find a Taylor series for f of x equals e to the 5x centered at 2. All right, so that's going to be a little bit more interesting because these are centered at 0. So let's see if I can just replace x with x minus 2, and let's see if it would work out. So let's kind of go back to the basics here and just derive it from scratch, all right, and see if it does end up being just the substituted version of x minus 2. Well, it's either 5x. Well, before we do that, if I just substitute a 5x in here for x, that's not going to quite do the trick because that would be still centered at 0, okay? So let's start with f of x equals e to the 5x, and we want to center it at 2. And the reason we would want to center it maybe at 2 is because maybe we're trying to approximate f of 2.1 instead of like f of 0.1. So if you choose a center that's relatively easy to evaluate but is still close to some number that you can find the value of, it makes sense to move the center. So f of 2 would be e to the 10th, right? F prime of x is going to be 5 e to the 5x. So that's going to be f prime of 2 is 5 e to the 10th. F double prime of x is going to be times another 5. Well, I'm not going to call it 25. I'm going to call it 5 squared. And you'll see why here in a second. It's just maybe lazy, if nothing else. 5 squared e to the 10th. And I think you kind of see a pattern emerging now. The third derivative is going to be another chain rule times another 5. So it's going to be 5 cubed e to the 5x. And then the third derivative at 2 will be 5 cubed e to the 10th. So on and so forth. So let's go ahead and write then the series. E to the 5x is equals or squiggles? If we're writing a series. Equals. Yeah, if we're doing a polynomial, then it's squiggles. But we're going to do the whole series. So we start off the exact same way. If it's a polynomial, we start off by writing the equation of what would be essentially the tangent line. So it's the y value, e to the 10th, and then plus the slope, which is f prime of 2, so plus 5 e to the 10th, times x minus the center. What's our center? 2. Right. So that would be the first degree Taylor polynomial approximation. That would be the tangent line. But now we're going to kick in the other terms. So now we're on the third, we're on x squared, so we're on the second derivative. So the numerator is 5 squared e to the 10th, and now it's over 2 factorial. So again, remember the derivatives at the center are just the numerators of the coefficients divided by the power factorial. Now that's x minus 2 squared. And we'll do one more here, plus 5 cubed e to the 10th over 3 factorial times x minus 2 cubed. And if you needed to generate more terms, perhaps maybe you'll see the pattern and you won't have to go through all this process. But it's said to write the general term. So now we have to go plus dot 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 plus, and now I have to see if I can capture the pattern term by term. So now you could see why instead of calling it 25 and 125, I just left it as a power of 5, because notice as the powers of 5 increase from 1, 2, and 3, those numbers are easily also indexed by the derivative number I'm on, or by the power of x, right? So when it's x minus 2 to the first, it's 5 to the first. When it's x minus 2 squared, it's 5 squared. In other words, the n value is also the power of n now that's on the 5. So if I'm going to capture the pattern, it looks like it's going to be 5 to the nth power, e to the 10th over n factorial times x minus 2 to the nth. Good. Plus dot dot dot. There you go. So because we were trying to write a function at 5x at a different center, we have to start over. you can't just shift over the function if you're going to change the center. Okay? You can replace the 5x with x, but it would still be centered at 0. So new center, new series. Okay, and that's it for now. Writing patterns. So again, when you're kind of like taking derivatives, try and keep everything, if you can, as an index in terms of what derivative you're on. So simplifying too much, you can kind of lose the pattern. All right, there are 4 special Maclaurin series that you have to know, and we've already been introduced to 3 of them in the previous section and in this section, e, sine, and cosine. But there's another one called 1 over 1 minus x. Okay? And 1 over 1 minus x is a pretty important one because it's kind of related to geometric series. If you remember for geometric series, for one that converged, how did we find the sum? The sum was always the first term over 1 minus the ratio, okay? And this is very closely related to that. It's the number 1 over 1 minus x. So once we learn what that one is, here are some of the things that we can actually do with the series. If we take the derivative or the integral of a series, it's going to be perfectly allowed. But there's one little caveat to that. Taking the derivative or the integral of a series will possibly change the interval of convergence, but not the radius of convergence, which means the endpoints might be affected. Now, for a function like sine of x, cosine x, and e to the x, which converge for all real numbers, that's not an issue. But for a series that only converges on a finite interval, like we talked about last time, if you take the derivative or the integral, all you have to do is retest the endpoints if you want to figure out what the new domain is or what the new interval of convergence is. So aside from derivatives and integrals, here are some of the things that we could do with a series. And we kind of did them with polynomials. You could substitute into a series for x. So you can replace x with 5x, x minus 2, whatever. You can multiply or divide this series by a constant and or a variable. So we saw that in the previous section. We multiplied through by x. You just do it for every term. You can actually add or subtract 2 series. That's going to be a little bit more interesting because how many terms do you have? Infinitely many. So there would have to be some kind of pattern where you could see what's happening. And as I just mentioned, you could either take the derivative or integrate a series and then retest the endpoints. And then one of the other things, which is a whole section in and of itself, is recognizing a series as a sum of a geometric power series. Okay, so let's see where that comes into play. Let's meet this guy right here. We know sine, we know cosine, we know e. This one is pretty important. Now, if we wanted to generate the power series for this, we could either A, do Taylor's rule, like we just did with e to the 5x centered at 2, or we can actually just listen carefully to what the question is asking us to do. What does this line tell us to do right here if you lean in? This horizontal line, it means divide. So this says 1 divided by 1 minus x. Well, let's see what that looks like. I'm going to add a page here. Add a page. All right, so this is a little mathematical aside. 1 divided by 1 minus x. Well, that's the same as 1 divided by 1 minus x. So notice what we're doing, as we do with all the series, if you've noticed, is write everything in increasing order of degree instead of descending order, like in Algebra 2. And the reason we're writing in ascending order is because we're generating terms starting with 0. So if I write this in ascending order on the outside, let's see how we do the division. How many times does 1 go into 1? Once, okay? And now if I distribute, I get 1 times 1 is 1, and then I get minus x. And then I subtract. So I change both signs. I get 0, and then if I add straight down, I get x. How many times does 1 go into x? In other words, what is x divided by 1? X times, so plus x. If I distribute from on high, I get x minus x squared. Change both signs, the x's cancel, you get x squared. How many times does 1 go into x squared? X squared times. Multiply from on high, you get x squared minus x cubed. Change both signs, you get x cubed. How many times does 1 go into x cubed? X cubed times. Do you see a pattern emerging? Yeah, all we're doing is long division, but is it ever going to end? No. It goes on forever. Okay? So this could have been like an Algebra 2 problem for y'all, and this could have been maybe your first experience with infinity, but maybe it didn't happen. So this is one way to get the power series for this right here. It is 1 plus x squared plus x cubed plus yada, yada, yada. Anyone want to guess what the general term is? X to the n plus dot, dot, dot. Very good. This is probably the easiest series in the whole wide world. Okay? Now notice that it is closely related to a geometric series. Here's why. If I write it in sigma notation, it would be from n equals 0 to infinity of x to the nth power. So if I want to know where this thing converges, and this is kind of getting into the next section, but it's okay. This is going to converge. Think about x as being the ratio. If I called that r instead of x, it would be a geometric series, right? It's basically something to a power of n. And I know that this is going to converge when the ratio, the absolute value of it is what? Less than 1, okay? So you can think of this as a geometric series with the absolute value of x being the ratio. Well, let me flip those around. The ratio is just the x, and it's going to converge whenever it's less than 1. So remember, our goal is to write it in this format. So we really have it in that format. So the radius of convergence is 1, and do you think we can include the endpoints? Do you think 1 to the n converges or diverges? 1 to the n is just plus 1 plus 1 plus 1. It diverges. If it were negative 1 to the n, it would alternate, plus 1 minus 1 plus 1 minus 1. So this thing converges only on the open interval from negative 1 to 1. Which kind of makes sense, right? Because that's what exponentials have to be, right? They have to be between 0 and 1 in function land. We can include negatives as well. But that makes it exponential decay, which makes it go to 0 faster. Now, if this truly then was a geometric sequence for values of x between negative 1 and 1, how do we find the sum of a convergent geometric series? It is equal to the first term, right, which is 1 all over 1 minus the ratio. And what's the ratio here? X. So very closely related. This is the geometric series for 1 over 1 minus x. And it converges for all x between negative 1 and 1. Pretty cool. So that is the other series that you need to memorize. And in the next section, we'll practice a lot more with that one. We can actually now find sums of series or power series that are of that form. Okay, so let's jump down to example 4. It says, if f of x is equal to that, find f prime and f prime of 0. Okay, first things first. So one of the things we could do, remember, is to take the derivative. So f prime of x should be equal to, term by term by term, we get 0 plus 1 plus, now remember, if I take the derivative of x squared, I'm going to get a 2 over 2 factorial. 2 over 2 factorial simplifies to, yeah, because 2 over 2 factorial is the same as 2 over 2 times 1 factorial, and so it'll divide out. So basically, 2 over 2 factorial is 1 factorial. So we're just going to get x over 1 factorial, which is, of course, just x, plus the derivative then would be 3 over 3 factorial. What's 3 over 3 factorial? 2 factorial, right? Yeah, I'm trying to get y'all to just give me this answer. 3 over 3 factorial is 3 over 3 times 2 factorial. 3's divide out. So anytime you have the same number that you're starting with, it's just the next factorial. So that would be x squared over 2 factorial. And for what it's worth, x to the 4th over 4 factorial then would be 4x cubed over 4 factorial, which would be 3 factorial, right? Okay, plus dot, dot, dot. Now here's what's cool about the nth term. You can take the derivative of the nth term just like you would each term. We're taking the derivative with respect to x. So using the power rule, that's going to be, I'll do it up here, n times x to the n minus 1 all over n factorial. But like we've been doing, what is n over n factorial? it's 1 over n minus 1 factorial, right? So we end up with x to the n minus 1 all over n minus 1 factorial. N minus 1 factorial. Plus dot, dot, dot. Okay? So there's the derivative. Now, what do you notice about the derivative compared with the original series? Same. It's the same. Term by term, there's a one-to-one correspondence. They match up. So why do they have different rules of sequences now? They're really not different rules of sequences, are they? We just had that conversation. They both capture the exact same pattern. One just starts at a different value of n. When you take the derivative, you lose a term, so you have to start at the n minus first term. But I could just as easily replace x to the n minus 1 over n minus 1 factorial with x to the n over n factorial. I could do that. Or x to the n plus 1 over n plus 1 factorial. So what is f prime of 0? Well, let's try that out. F prime of 0 is 1 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. So it's 1. So now the question says, do you recognize this familiar function? And of course, yeah, you do recognize it. You should recognize it from the top. We just did that, right? This is e to the x. And what is the derivative of e to the x? E to the x. We just kind of proved it works with the Taylor series as well. The derivative of this polynomial is the exact same polynomial. And of course, e to the 0 is 1. That's pretty neat. Now, in this case, we don't have to check where the derivative converges because the endpoints are unaffected because it's all real numbers. But in general, if the function we started with converged, let's say, on a closed interval, then on the derivative, we'd have to check the endpoints because it may be now on the open interval. The radius doesn't change, but the interval might. The endpoints can change. Pretty sweet how this all kind of works out. Example 5. If f is equal to that, and big F is the integral, and f of 0 equals 1, find big F of x. All right, first things first. Let's go ahead and integrate both sides with respect to x. And notice the rule of sequences there. So the antiderivative of little f is big F. And leave a little space on the right side, past the equal sign. What would be the antiderivative of negative x? What's x to the first? So you would add 1 to get 2 and divide by the new exponent. So you'd have negative x squared over 2. And then the next term, you'd have plus. You'd have x to the fourth. And when you divide by 4, what's 4 times 3 factorial? 4 factorial. And 2 factorial is the same as 2, so let me just throw that on there. The next term would be minus x to the fifth becomes x to the sixth. And then I divide by the new exponent of, or the new exponent of 6. 6 times 5 factorial is 6 factorial. And then plus dot, 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 plus. Now, we could do the same thing on the rule of sequence. Here's the deal, though. I have to be careful with my alternator. The alternator, you always want to check. So it's either going to still be to the n or n plus 1. But let's go ahead and do the power rule here. It's going to be x to the 2n plus 1, which is what? 2n plus 2, divided by the new exponent of 2n plus 2. Well, what's 2n plus 2 times 2n plus 1 factorial? It should be 2n plus 2 factorial, right? We're just adding the very next factor so we can put the factorial, plus dot, dot, dot. Now, what was the last thing that we always did when we found antiderivatives? Plus c. Are we ever going to finish taking the antiderivative of all the terms to put a plus c at the end? No. So where should we put our plus c? We should put it in the front. We are writing things in ascending order after all. So c is a constant. It's a 0-degree term. So that's why we left the space there. We'll just put a c in the front. Okay, so now let's check if we capture the pattern what this has to be. When n is 0, we're going to get 2n plus, we're going to get 2. That's going to be the squared term. I'm going to get this. Is my squared term positive or negative? Negative. So if when n is 0, it doesn't matter where we're starting, I'm going to get the squared term, which has to be negative. So will this be negative 1 to the n or n plus 1? When n is 0, I want it to be negative. So right now, I have to put a plus 1 there. Yeah. All right, so always check your alternator. Now, how are we going to find the C value? Yeah, you need an initial condition, and it gave it to us. So just like before, when f of 0 equals 1, we'll say at the point 0, 1, we'll say 1 equals C, and now I plug in a 0 for all the other x's, and I get minus 0 plus 0, minus 0 plus 0, so C equals 1. So, big F of x must equal 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Those are the first three now non-zero terms. I'll go ahead and write the next one as well. X to the 6 over 6 factorial plus dot 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 plus negative 1 to the n plus 1 x to the 2n plus 2 all over 2n plus 2 factorial plus dot dot dot. Now, do you recognize, once we have that initial condition, do you recognize the function? Yeah, it's cosine. It's cosine. What would be the original function then? Yeah, the original function is negative sine. Because notice the terms are opposite signs from what they normally were. So if you take sine and multiply through by negative 1, you get them to alternate the other way. And of course, what is the antiderivative of negative sine? Positive cosine. Yeah, positive cosine. And we just kind of proved that right there. All right. Pretty interesting how these polynomials behave in all the expected ways that all these functions we've been working with all year behave. Pretty interesting. Find the Maclaurin series for sine of x squared and the general term. So we'll probably have to do this after lunch. Okay? And I think we'll be able to finish these notes today. We got 6, 7, 8, and 9. 9 is pretty nice. 9 is pretty nice. We're going to derive Euler's identity. And if you've read my website, if I ever were to get a tattoo, this would be the first one I'd get. I don't have one, but tempted. That would be it. Maybe right across my forehead. Kind of in reverse, like ambulance. So when I'm driving, people look in the rearview mirror and they see that. All right. Have a great lunch.